So for this video lecture, I'm going to cover a little bit some more special cases on electric fields. I'll review a parallel plate capacitor, and we'll look at some extra with conductors and insulators and the electric fields they produce. And this follows along in your textbook. Some of the chapters use sections you may have also read, but we also move into section 18.8. So while I've briefly touched on parallel plate capacitors, I kind of wanted to talk about them a little bit more. What they really are two large electrodes that have opposite charges. And by electrodes, I mean just a plate with where charge is allowed to build. And the two plates themselves, or the electrodes, are much greater in size and area than they are in the distance apart. So the spacing, as we said, it doesn't matter. That is only true within a situation where the two plates themselves are large compared to that, or are much greater compared to that small spacing. Now, when it does exist that it's a small spacing compared to the great size, there's a uniform electric field in the middle, and that's the main key idea from what this happens, because when this occurs, you get this uniform field, and a moving charge, or charge that is moving through this thing, will be deflected one way or another. And so what happens is these are used in a lot of applications to create different effects. You have a capacitor like this in an old cathode ray TV. You have a capacitor like this in if you have like one of those ion breeze things that supposedly clean out the air. Those things are air purifiers. They use this technology here, and they use this idea in order to purify air and to accomplish other tasks that we're familiar with. We'll see more examples of this as we move on. Now, when we look at conductors and different types of materials here, we're going to pay special attention to the electric field around them. And within a conductor, the charge is continually spread out throughout the material, so it's uniform on the surface. And because it's uniform on the surface, all the charge within, for example, a metal ball will move to the surface because inside, it wants to get as far away from each other. So inside, the electric field will be zero because it's actually canceled out by all the other charge on the opposite side or whatever. So the important idea is within a conductor, a circular spherical conductor, the electric field is zero. And actually, within any conducting material, the electric field is going to be zero. So, and if you look at the field lines going into a conductor, they're always going to be perpendicular to it. So as they curve towards it or curve away, they're always perpendicular when they contact the surface. Due to the fact that the electrons are free to move within a conductor, and as they move to the outside edge when it becomes charged or placed in an electric field, the inside of any conductor, the electric field there becomes zero. In this case, the applications for this are whether it's solid or there's a cavity on the inside, because it will cancel out any electric field set up as the charges will redistribute themselves. So since the electrons are, again, free to move within the conductor and they dissipate around the surface, I guess dissipate is kind of the wrong word, or spread out, they move to the surface, there is no electric field within a shielded conductor. This doesn't apply to insulators because the electrons are not free to move around. They're within the atom, they're generally free, or within the molecule right there, they can kind of move to one side or another, but they're not free to move around from molecule to molecule to the level that they are in a conductor. So just some ideas behind the electric field within conductors and insulators. A couple of questions from tonight's video. First, what is the electric field inside a conductor? This is probably one of the more important questions and more important ideas that you'll need to pretty much just straight up memorize. And second, describe how charge is distributed on the surface of a conductor. And a follow-up question to that is, why do you think charge is distributed this way? So I want you to First, describe how it's distributed and how it's on a conducting shape or anything like that, and then tell me why you think it is this way. All right? And thank you very much once again. Have a good night. See you in class.